Hi, my name is Nathan Lacroix. I am from ETH Zurich, and it's a pleasure for me to give this talk as part of the Quantum 2020 conference. During the next 15 minutes, I will explain to you how we used hardware-efficient quantum operations, namely a continuous gate set, to improve the performance of deep quantum optimization algorithms. I will then provide some experimental data where we use one of those gate sets to solve an optimization problem on a 7-qubit superconducting quantum processor. This work was performed at ETH Zurich and was led by Andreas Wallraff and was also in collaboration with Agustin Di Paolo and Alexandre Blais from the University of Sherbrooke. I will start my presentation with a brief introduction about the relevance of continuous gate sets for near-term quantum computing, and starts with the idea that there's a clear interest in developing application for near-term noisy intermediate-scale quantum computers. And in doing so, the community faces two major challenges. Firstly, that current quantum computers have a low number of qubits, and secondly, which is what we will focus on for the rest of the talk, that there's only a limited number of operations that can be executed on the quantum hardware. And this is because we do not have quantum error correction, and therefore imperfect control and decoherence introduce noise. This is especially harmful in cases where high-level quantum operations are decomposed into a longer sequence of gates that can actually be run on the quantum computer. So in analogy to how a classical computer could, for instance, decompose an addition operation into a sequence of NAND gates, a quantum computer typically uses a standard gate set, which consists of single qubit gates and one or several 2-qubit gates, such as the CZ gate or the swap gate, to decompose high-level quantum operations into a gate sequence that is executed on the quantum computer. And in doing so, the gate sequence can get a lot longer because of the decomposition. So the idea of continuous gate sets is to harness the structure of the algorithm that has to be executed to tailor the gate set and thereby reduce the number of gates that are in the gate sequence. So this is done by choosing a gate set that matches the operations that are done in the algorithm. And this idea has been investigated already by Google, IBM, and Rigetti for various purposes, including quantum chemistry and quantum simulations. But in the scope of this talk, we will focus on continuous gate sets that we have developed for the quantum approximate optimization algorithm, which I will now briefly give a reminder of. So the quantum approximate optimization algorithm, or QAOA, is a hybrid quantum classical algorithm, meaning that part of the algorithm is performed by a classical computer. It finds approximate solutions to combinatorial problems by mapping the combinatorial problem to an Ising Hamiltonian, such that the ground state of the Ising Hamiltonian is the solution to the combinatorial problem. It then tries to find the ground state by preparing an ansatz state based on p layers of two alternating unitaries. The first unitary is the phase separation operator, which is a function of the problem Hamiltonian C, and a layer-dependent continuous variational parameter called gamma. The second unitary is a mixing operator UB, which is a function of the mixing Hamiltonian B, which consists of single qubit X rotations, and a variational parameter called beta. The ansatz state is then measured and then used by a classical optimizer to measure the expectation value of C for the ansatz state, and the classical optimizer then updates the variational parameters to minimize the energy of the system. One important fact to point out is that the performance of the algorithm is largely dependent on the number of layers that are applied in the algorithm, and typically more layers allow to solve more complex problems. So the key part of the gate sequence, which is where the continuous gate set comes into play, is in the phase separation operator. One observation to make here is that all terms in C commute because C is diagonal on the Z basis, and therefore each term in C can be considered individually. Also, for the purpose of this talk, we will not be looking at single qubit bias field, and therefore C can be expressed as a sum of qubit-qubit terms with qubit-qubit coupling Jij. If we look at one of these terms, we see that the operator is expressed as a ZZ term with an additional phase factor that is continuous and that depends on the variational parameter gamma. Because the phase factor is continuous, the operator typically cannot be executed directly on the quantum computer and instead has to be decomposed into a longer sequence, including two qubit gates, for example, CZ gates or controlled Z gate, which add a phase of pi on the 1-1 state and some additional single qubit rotations. The alternative that we suggest here is to use a continuous gate set that use arbitrary phase controlled Z rotations, which essentially add a desirable phase angle phi on the 1-1 state. And using this continuous gate set, we can then implement the operator with simply 1 2 qubit gates and 2 single qubit gates. So this is then much shorter in execution time on the quantum computer. Then if we look at the mixing operator, we use the same for the two approaches, which are essentially only single qubit gates. To implement the gates with superconducting qubits, we use frequency tunable transmods, which are artificial atoms with discrete energy levels that we can then address with microwave pulses to implement single qubit gates. For the 2 qubit gates, we use a standard technique to implement a controlled Z gate that relies on a non-computational state. The idea is to use a flux pulse on one of the 2 qubits that changes the excitation frequency of that qubit such that the 2-0 state comes close in resonance with the 1-1 state. This starts a coherent population exchange between the two states, and after one full oscillation period, the population that was initially in the 1-1 state is back into the 1-1 state, but with an additional phase factor of pi. To implement this on the quantum computer, we need to calibrate both the length and the amplitude of the flux pulse. And we do this by looking at the excited state population of the qubit that goes out of the computational space. And for the parameters coordinate indicated with this green diamond here, you see that the population is fully back into the excited state and not the second excited state. And it also yields a conditional phase of pi. What we do afterwards is that we simply extend this scheme to the arbitrary controlled phase rotation, CZ phi gate. And we do this by adding a frequency detuning during the interaction. So this frequency detuning delta ensures that there's only a partial population exchange, and therefore the phase collected is also different from pi. And by sweeping delta, we can then essentially achieve any conditional phase between 0 and 2 pi. Okay, so now that we have all the different building blocks of the QAOA gate sequence, we can look for a combinatorial problem to solve with the 7-qubit quantum processor that we depict here on the right. We decide to look at the exact cover problem, which is an NP-complete problem, and each instance of the exact cover can be represented with a matrix, here, for example, shown in B. The idea is to find whether there is a combination of columns of this matrix such that each row of the matrix is included exactly once. For each column, rows that are included are indicated with a dot. So in this case, selecting columns A1 and A2 would together form a valid solution of the exact cover because together they cover the 3 rows of the matrix. Alternatively, we could also select column B2, which by its own covers the 3 rows of the matrix. Each of those columns are then mapped to one of the qubits of the quantum processor, and we indicate whether a column or qubit is part of the solution with a binary encoding. So 1 means that the column is included, and 0 means that the column is not part of the solutions. So the 2 solution state in this case would be the 110 state and the 001 state. We can then build a bigger problem instance that makes use of the 7 qubits of the quantum processor, which also has 2 solutions, namely the 4 columns with qubits A1, A2, A3, A4, and B1, B2, B3. So those are the two solutions, and the corresponding mapping to Hamiltonians are depicted here on the slide. We start by implementing the 3-qubit problem instance with a single QoA layer. And in that case, there are only two variational parameters, gamma and beta. And in this case, we can then easily map out the value of the cost function for the entire parameter space. So we use 20,000 single-shot measurements for each parameter pair, and we compute the expectation value of the cost and plot it here on the left-hand side and compare it to a noise-free simulation. We see that the measurement is in good qualitative agreement with the simulation, as it shows the same minima and maxima, and the residual features that we see, for example, this diagonal feature here, can be explained by decoherence and residual ZZ coupling. So what we then do is that we embed this cost function in a classical Nelder-Mead optimizer to demonstrate the end-to-end QoA procedure. And in that case, we initialize gamma and beta at random. So we show here 3 selected random initialization with black triangles. And we let the Nelder-Mead optimizer find a set of parameters that minimizes the energy. What we see in most cases is the behavior here in the upper left, where the optimization trace converges to the global minimum of the optimization landscape. However, in some cases, we do notice that the optimization traces converge to local minima. Another important observation is that even in the noise-free simulation case, we do not reach the ground state energy of minus 1.5 with a single layer, which then motivates the use of QoA implementations with more than one layer for this problem instance. So we investigate this further by increasing the number of layers in the QoA implementation. But in that case, the number of variational parameters grows, and therefore we cannot visualize the entire parameter space anymore. So what we do is that we look at the output register probability distribution for pre-optimized variational parameters. And we show here the distributions for 1, 2, and 3 layers. The filled bars correspond to the measurements, and the highlighted colors correspond to the solution states of the problem instance. Those 3 measurements were performed with a direct implementation of the arbitrary phase gate, namely the continuous gate set, and we see that indeed, with increasing number of layers, the probability of measuring one of the 2 solution states increases. However, we see that the fidelity with respect to a noise-free simulation, here indicated with a black wireframe, decreases. And we also see that the deviation from the ideal measurement are in good agreement with master equation simulations, which are here plotted in red. When we compare this to the decomposed implementation, which uses the standard gate set, we see that the direct implementation is always better than the latter because it has a shorter execution time. We have an equivalent dataset for the 7-qubit problem instance, but it has many more states, and therefore we do not show it here. But to be able to compare both approaches and condense the information in a single plot, we look at the improvement of the success probability with an increased number of QoA layers. We define the enhancement of the success probability as PS over PU, where PU is the uniform probability distribution over all possible states, and PS is a probability of measuring a solution state. What we see in the 3-qubit problem instance, which is depicted here on the left, is that in the noise-free simulation case, we need 3 layers to reach a success probability of 1. We also see that the direct implementation peaks at p equals 3, and that it always outperforms the decomposed implementation, which does not use the continuous gate set. For the 7-qubit problem instance, this effect is further amplified because even in the noise-free simulation case, we require more than 6 layers to reach unit success probability, and therefore the direct implementation which has a much shorter execution time than the decomposed implementation for the same number of layers, can benefit from additional layers, and it thereby achieves a 3 times higher success probability than the decomposed implementation. Finally, I would like to point out that for long sequences, both approaches show comparable performance. So for example, for 5 microseconds here and 5 microseconds of the decomposed implementation, we see that the performance is roughly similar, which indeed indicates that we are in the end limited by decoherence. So the take-home message that I would like you to remember from this presentation is that continuous arbitrary phase gates can significantly improve the efficiency of gate sequences for variational quantum algorithms such as QAOA. And we have demonstrated this here with 2 instances of the exact cover problem using 3 and 7 qubits and requiring up to 9 QAOA layers. We have also used up to 400 gates and shown peak performance above p equals 1. So our plans for the future are to explore larger problem instances and also investigate the advantages of this continuous gate set as we progress towards more complex experiments. With this, I thank you very much for your attention, and I am looking forward to answering your questions during the Q&A live sessions.